In this video, we look at example 5 from section 3.1 on the definite integral. So for example 5, it says the table shows rates of population growth for a town, Berrytown, for several years. Use this table to estimate the total population growth from 1970 to 2000. So just to get a sense of what's going on here, our first row is telling us the year. Our next row is telling us the rate of population growth. So that means thousands of people per year that were added to the city. So for this problem, we're not given the explicit function, we're just given the values or the rate of population growth at certain times. So we're going to use a Riemann sum to compute the total growth of population. So just to recall, I always like to draw a little sketch for us. So for us, it's as if we're graphing a function here where we have time on the horizontal axis. We can even plot some points here. So I have, let's say this is 197 or 1970, 1980, 1990, and 2000. Okay, and then we're told that we'll even label some axes here. The 1, 2, 2.5 is like there. And so we're told that 1970, we have about 1.5. 1980, we have about 1.9. In 1990, we have about 2.2. And then 2000, we have about 2.4. Okay, so something like this. We just know these discrete values. So because this graph or this function here is telling us the change of thousands of people per year, if we determine the area underneath our curve, that will tell us then the total amount of people that have come into the town between those years of 1970 and 2000. So I want you to try to approximate that area by using a Riemann sum. So the Riemann sum I want you to try to use is use left endpoints. So I'll write that out. Approximate the population growth from 1970 to 2000 using, and we're going to say 4 to keep things kind of simple and similar to what we've seen already. Actually, rather 4, we'll use 3 because we have 3 possible chunks here. Using 3 left point rectangles. So at this point, I want you to pause the video and try to find or approximate that population growth using 3 left point rectangles. So when you're ready, let's look together. So we're going to go through this pretty quick. Feel free to pause the video at any time or rewatch any parts. So I'm just going to draw a little sketch of what hypothetically what our graph could look like here. So it looks something like this. So first what I'm going to do is draw in those left endpoint rectangles. So we have one here, and one here. So we just have 3 chunks here, and their heights are given by those function values. So I'm going to erase some things just to clean up here, give me more room. So left endpoints. So what's going to be the width of each rectangle? Well, my years are going from 1970 to 1980. So I have a chunk of 10 for each rectangle. So my change is going to be 10 for each. The first one has a height of the output value at 1970. So that would be 1.5. My next rectangle has an endpoint where 1980 is, so 1.5. 0.9. So my next rectangle would be 10 times 1.9. And my final rectangle would have a width of 10. And then that height would be given by the value of the population, the change of population or the rate of change at 1990. So that would be 2.2. So we could add all these up. We'd get 15 plus 19 plus 22. And when we take the sum, we would add up and get 56. So take a look, check your work, see if you're getting 56. And what would the units be here? Well, we're multiplying years by thousands of people per year. So this would be 56,000 people. We can clean up our spelling here as well. Okay. So after you've checked your work, now I want to see if you can do this problem again, but use right endpoints. So take a moment, pause the video, and I'd like you to draw in the 3 rectangles that you're going to use, and then compute the area by using right endpoints. After you've done that, let's compare work. So now our rectangles, their height is going to be determined by the endpoint on the right. So this first rectangle would be determined not by 1970, but the output at 1980. So we can draw that in here. Like this. So let's determine the areas of each of those. Again, our width is going to be 10, but now the first rectangle has a height at the output at 1980, so a height of 1.9. Next rectangle has a height of 2.2, and our final rectangle has a height at 2.4. So our areas would be 19, 22, and 24. Now, when we add all those up, we should be getting 65,000 people. So what do we notice about the left endpoint and the right endpoint? Well, the left endpoint, those areas are all underneath the curve or are a little bit less than the area actually under the curve. While the right endpoints in this case are all larger. They cover the curve plus a little more. So we'd say that in this case, the left endpoint is an underestimate. And the right endpoints do an overestimate. So we would find the total population growth between these years somewhere in between 56 and 65,000. So I'm going to write that here. So the total population growth for our Barre town is between 56 and 65,000 people. So just to recall, this value tells us how much our population grew between these years. So it doesn't tell us anything about what value or how much our population is actually at. It just tells us about the change or growth in population. And again, that's just because if we have a rate of change graph, then those accumulated rates of change tell us how much we change in total. So the total change here.